Hi guys, we're going to do a review for tomorrow's quiz. So we're going to go over several different questions, okay, and concepts. So we'll work quickly. You're welcome to obviously pause the video at any time and go back and look at the questions, okay? So we start off with Newton's third law, and we want to be able to describe the paradox that occurs, because when we look at Newton's first law, it says every action has an equal and opposite reaction. So if our action is equal to our reaction, then everything is in equilibrium. And if the sum of the forces equals 0, then the acceleration equals 0. So obviously this object can accelerate, so there's something going on with the forces there. So let's start off with looking at the action-reaction pairs. And so the first action I think we see is the boy pulls on the cart. So there's a force over here going in this direction, and that's the boy on the cart. All right, and so if that's an action force, then there is also a reaction to that occurring. So if the boy pulls on the cart, then the reaction is the cart on the boy. All right, so that is our action and then our reaction. All right, what other action is going on? Well, there's something else going on with the cart, and that is the friction going on with the cart. Okay, so we know that the boy's pulling the cart in this direction. So we start off with the ground has friction on the cart. So the ground has friction on the cart. That would be our force here. Okay, and then the opposite force to that would be the cart has friction on the ground. All right, so if the cart has friction, then the ground is creating that, so you got equal but opposite. So now we have, let's only draw the forces on the cart. So if we draw the correct free body diagram over here for the cart, we know that the boy pulls on the cart, and we know that there's friction on the cart from the ground. So in this direction we have friction, ground on cart. So we could just simply say that this is not in equilibrium because the boy pulls on the cart with more force than friction, which is the ground acting on the cart, and therefore he can pull it. Now if this friction got bigger and bigger and bigger, then he would have to pull with more and more force to overcome it and to make it move. So Newton's third law, it seems to be a paradox. It seems to be that there are no forces able to make an object accelerate because everything is equal but opposite. But if you take into consideration a free body diagram, only the forces acting on the cart, you can see that that object easily moves. All right, we're going to quickly go through force normal. We have two cases, case 1 and case 2. And then we have 3 examples of case 1. So force normal for case 1, a horizontal surface. So if we have a box sitting on a table, and let's say the weight of that box is 10 newtons, okay? Now be sure this is weight, which is in newtons. Mass is in kilograms. So if you already get a newtons, that's a force, and weight is a force. So if this has a weight of 10 newtons, then the force normal is 10 newtons as well. When you're on a horizontal surface, force normal equals the weight of the object. All right, what about if we have some additional weight on it or someone's pushing at an angle? So if we start over here and we have our box, and again we'll give that 10 newtons, okay, going down. So let's say we add another box on top of it, and that box has a weight of 5 newtons, okay? So we got 10 newtons, our original box, and then we have a new box that's 5 newtons. So the table must exert an upward force called force normal, and in this case it would be 10 plus 5, or force normal 15 newtons. Okay, so now when you have an object that has additional weight, you would add that, and the force normal would increase. All right, so let's look at this scenario here. We have a box, and let's say we have somebody applying a force pushing on this box at an angle. Okay, so they're applying a force at an angle right here. We'll say this is maybe 20 degrees. All right, so this box, we'll give it a weight of 10 newtons. So the force normal, because it's a horizontal surface, equals the weight. But because he's pushing down, it adds more force to it, and it adds the force that he has in the y direction. So we need to find this little force right here, which is the force in the y direction, okay? And because he's pushing down, that goes down. So you should remember by now the force in the y is the sine of theta times the force he applies. So force is the sine of 20 degrees, and we'll call this 10 newtons. And so the force in the y direction is the sine of 20 times 10. So we get our little calculator here, and 20 sine, clear, we've got to do the sine first on this calculator, times 10, and we get 3.4. So the weight is 10 newtons, the force y is 3.4 newtons, and so the force normal is 13.4 newtons, okay? All right, so when we have a horizontal surface with additional weight or pushing, the force normal goes up, increases. All right, let's look at the force normal when we're pulling up or pulling at some angle. So let's say we have this box sitting on a table, and we have some type of pulley system attached to it, and we're over here pulling this pulley down, okay? All right, so the weight of this box is, again, 10 newtons. We'll give that the weight. So force normal on a horizontal surface equals the weight, but in this case, because this rope is going up, we know that it's decreasing. And we'll say that this is 3 newtons. I don't know, we just give it a number. Somebody's pulling up with 3 newtons. So now the force normal would be minus the force in the y direction, which in this case, you don't have to do any trig because it's straight up and down. So the force normal would equal 10 newtons minus 3 newtons, or 7 newtons. All right, let's look at one where we have someone, a box, and someone's pulling this, okay? And they're pulling this at an angle. We'll call that 20 degrees. We'll call this 10 newtons here, and the weight of the box is still 10 newtons. So again, its horizontal surface force normal equals the weight of the box, but we're pulling now. So now this F of y goes up, okay? In our previous example, the F of y was going down because we're pushing. Now the F of y is going up because we're pulling, okay? So we would actually, the weight minus the F of y. So based on our, again, the F of y is the sine component. So based on our earlier math, we would say 10 newtons. Now we're going to minus that 3.4, okay, where F of y is equal to the sine of 20 times the 10 newtons that he's pulling with. So our force normal in this case is 6.6. Let's check that. 10 minus 3.4. 6.6, okay? All right, so those are our examples for that. Now we're on to case 2. In case 2, we're looking at an object on an incline. So here we have our incline, and we'll just make this a 25 degrees. So if we have our object, and let's say it has a weight, still using that weight of 10 newtons. Now remember, to get that weight, we did mass times gravity. But this is already in newtons, so we don't have to do anything there to get it. All right, so 25 newtons. So we have 2 forces here when it's on an incline. One of those forces is force parallel. And force parallel is the force due to gravity to make it slide down a ramp. And there's a second force. It's down here. It's called force perpendicular. And force perpendicular is the force due to gravity pulling it into the box there. So now we want to find here our force here, which is called force normal. So the force normal on an incline, force normal, is equal to force perpendicular. And the force perpendicular is the cosine of theta times the weight of the object. So force normal in this case would equal the cosine of 25 times 10 newtons. And so force normal equals, and so we can come over here quickly and clear that out and go cosine 25 times 10, and we get 9.06 newtons. And that is our force normal on an incline. So for tomorrow's quiz, we'll only give you these types of examples for force normal. So tomorrow you'll only have either horizontal with a weight added, or someone pushing, which also increases force normal. Horizontal with someone pulling up, or someone pulling at an angle. In those cases, force normal decreases. Or case number 2, where we find that it's on an odd angle, and then it's simply the cosine component of the weight. All right? Force normal. From force normal, we dig into force of friction. So force of friction, let's answer these questions quickly. What are 2 things that manipulate friction? So we discussed this in class today, trying to come up with a good answer. And the 2 things that manipulate friction are the surface and the weight of an object. Okay? Now, but when you look at surface, or mu, and that is the symbol for the coefficient of friction. The coefficient of friction is mu. So the 2 things that affect gravity, the 2 things that manipulate friction are the surface of the object and the weight of the object. Now, when we talk about surface, there's 2 things that control that. The 2 things that control mu are surface area and surface type. Okay? Surface area and surface type. What are 2 types of friction and defined? So our 2 types of friction are static and kinetic. Okay, static and kinetic. And so if we define those simply, static is non-moving and kinetic is moving. All right, non-moving and moving friction. So kinetic is always less. The kinetic friction is always less. Describe a case where static friction is at a max on an incline. So if we're on an incline and we know it's static, so static is non-moving. Okay, so here's our box. It must have static friction, and we're labeling that coming up. So here's our static friction right there, and that's our yellow vector. And so what else is happening there, right? We remember that the weight of the object creates 2 parts, right? One of those parts is called force parallel, or force applied. It's the force applied by gravity, which is pulling it down. So to describe a case where static friction at its max is the angle where the box is at rest. It is just before moving. It's the maximum angle where the box is at rest just before moving, so force of friction equals the force applied by gravity, which we know is force parallel. Okay? So when the force of friction is equal to force parallel, that's when the maximum angle just before that box starts to move. Okay? All right. Number 4. Describe the forces and acceleration of a box when kinetic friction is equal to applied force. All right. So if kinetic friction is equal to the applied force, and it doesn't matter if it's on an incline or a flat surface, but for ease of diagramming, we just draw this on a flat surface. So we have a force applied, maybe 10 newtons. Then opposite that, we have a force of friction, and we'll call that 10 newtons. Is the box moving? Yes. If it's kinetic friction, so this would be kinetic. If it's kinetic friction, then this friction over here means that the box is moving. To keep it moving, you must pull with 10 newtons. So think about that. You must pull with 10 newtons, otherwise the friction takes over and slows the box down. So to keep the box moving at constant speed. So describe the forces. Force of friction is equal to the force applied. Describe the acceleration. Acceleration equals 0 because the system is in equilibrium. All right, equilibrium. Describe the things gravity does when an object is on an incline. So we mentioned that just a moment ago. But gravity does two things. Here's the weight. It does one thing, pulls it down, force parallel, pulls it into the ramp, force perpendicular. So force parallel is the sine component of the weight, and it pulls down the ramp. And then the force perpendicular, which is the cosine component of the weight, and it pulls into the ramp. And that force into the ramp creates force normal. All right? So describe the two forces that gravity creates. Some of gravity pulls it down the ramp, and some of gravity pulls it into the ramp. All right, let's look at a couple quick calculations. All right, so we'll start off by simply calculating the acceleration. All right, calculate the acceleration of a box. Well, remember Newton's second law says the sum of all the forces. Okay, the sum of all the forces makes a mass accelerate. So if we have a box and somebody's pulling with 15 newtons, and somebody else, or friction, is acting with, say, 10 newtons, and we'll give this a box of 5 kilograms. So remember, this is a common mistake. Kilograms is a mass. So the sum of the forces acting on this box, which is 15 newtons, minus 10 newtons, because they're going in opposite directions, so we subtract them, is 5 newtons. And 5 newtons is what makes a 5 kilogram object accelerate. So mass times acceleration, where the mass is 5 kilograms. So the acceleration in this box is divided by 5, 1 meter per second squared. That is our acceleration in that case. Now, we can do a lot of things to calculate force of friction and all that. For now, we just start with calculating the acceleration of a box. We could say, if it has, let's look down here at this example where we want to calculate the coefficient of friction, okay? So in this case, we want to calculate the coefficient of friction. So we have a box, and it has again, we'll do a mass of 5 kilograms, okay? And so the weight would equal mass times, the weight would equal mass times gravity. So 5 kilograms times 9.81. The weight of this box is going to be 5 times 9.81. And I get 49.05. So we'll just go with 49 newtons for ease of numbers here. We don't get too hung up on the decimals for this case. All right, and so let's say we have, this is static, and it's a force applied of, let's say, let me think about this for a second. Force applied, we'll go say 55 newtons, okay? So there's a force applied 55 newtons. And if it's static, that means that 55 newtons has got to equal the force of friction. And it's the force just before it moves. So we're pulling on this box with 55, and the instant before it moves, we know it takes 55 force of friction. Okay? So in this scenario, static object at rest, when the force applied is going to be equal to the force of friction, this would be true. So there's one vector we're missing, and that is our force normal. So we've already decided that force normal on a flat horizontal surface is equal to the weight. So force normal is equal to 49 newtons. And then we know from our formula that force of friction is mu times force normal. So force of friction we decided was 55 because the applied force had to equal that friction force, equals mu times force normal, and our force normal is 49 newtons, okay? And so we'll just divide by 49, and we get a mu of 55 divided by 49, and we get 1.12. Now, I just made these numbers up quickly, so we come up with a little bit of an error here, and that is the force of friction is greater than the force normal because I made these numbers up. So that's creating us a little bit of problem here, okay? So the force normal is mass times gravity, 49 newtons. And if you pull with 55, the coefficient of friction has got to be really high. And so we do get a really high number. So this thing's got a lot of friction on it. So we've got to pull much harder to move it, all right? All right, good deal. So let's now look at the acceleration of a box on an incline, okay? Calculate the acceleration of a box on an incline, all right? So we have our box here. We'll go ahead and give this thing, 60-degree incline. So we have it going right here. We have our first force coming down. What's that first force? Oh, weight. Mass times gravity. And so for ease of calculation, let's just make this 5 kilograms times 9.81. So we know the weight of the box from our previous problem is going to be simply 49 newtons. All right. So now we have the box trying to slide down. Remember, there's that force parallel where gravity is trying to pull the box down. Then there's that other force where gravity is trying to pull the box into the ramp. That's called force perpendicular. Opposite force perpendicular is our force normal. Okay. And then there's some force of friction going up the ramp. So in this case, let's say that mu is 0.2. So our mu is 0.2. That's a given. Mu is 0.2. Coefficient of friction is 0.2. So the best way to just start solving these individual pieces. So let's start off with force perpendicular. So the force perpendicular is the cosine of the angle times the weight of the box. So force perpendicular is going to be the cosine of 60 degrees times 49. That is the weight of our box. So force perpendicular is, clear this out, go cosine 60 times 49, and we get 24.5 newtons. Now the force perpendicular is going to be equal to the force normal, okay? All right, now we can go ahead and jump from there if we want to. So we got force perpendicular, and now we know force normal. Okay. Let's go ahead and find this force of friction. So the formula for force of friction equals mu times force normal. So the force of friction is 0.2 times 24.5. Okay, so we bring that over here and go times 0.2. And so we have a force of friction of 4.9 newtons. So force of friction is 4.9 newtons, okay? So we know these forces are equal but opposite, force perpendicular and force normal. So those are equal and opposite forces. They balance each other out. So what we now know is force normal is 4.9. So the last piece to find is how much force is gravity exerting down the hill? How much force does gravity have in this direction? And that's our force parallel. So force parallel is simply the sine of the theta times weight. So it's the sine of 60 degrees times the weight, which we know is 49 newtons. So force parallel is the sine of 60. So we'll clear that out and we'll go sine 60 times 49, and we get 42.4. All right, so we have 42.4 newtons going down the ramp. So I hope you guys see this. We got gravity's pulling it down with 42.4, and it's creating a friction of 4.9. So remember Newton's second law. It's the sum of the forces makes a mass accelerate. So the sum of the forces, that's supposed to be a sigma, the sum of the forces is 42.4 newtons down the ramp, and then minus the 4.9 newtons, or friction, is going to equal, the sum of the forces is going to equal 42.4 minus 4.9 and 37.5. Now 37.5 newtons will make a massive object, which we decided was 5 kilograms in the beginning, 5 kilograms, and it will make it accelerate at some number. So we just divide by 5, and we get the acceleration of the box, okay? So we go 37.5, and we'll simply divide that by 5, and we find that it is 7.5 meters per second squared, okay? So the acceleration of a box on a 60-degree incline with a mass of 5. So be sure you know that this was a given. The blue was a given. The 60 degrees were given. And from those two numbers, I were able to solve all the different pieces. Okay, excuse me. We also had a coefficient of 0.2. So the givens were the mass, the angle, and the mu. And from those, I was able to solve for the acceleration of the box down the ramp. All right, guys, so that's a review for tomorrow's quiz. So you can go back and watch the other videos that I've submitted and uploaded for additional help. All right, guys, see you guys tomorrow.